This is an overview of IRSA for Priya Hasan's Astronomy from Archival Data program. So just as an introduction to what astronomical archives are, it is really true that there are more data than professional astronomers can really hope to completely mine, and there's more data coming in literally all the time. So yes, it's true that professional astronomers are going to pull off the easy-to-do science, the low-hanging fruit, but there's plenty of good science still in the archives. And any facility that comes from public funding, at least US government public funding, is supposed to have a publicly accessible archive, which means that, since the taxpayers already paid for these data, those data also belong to the taxpayers. NASA is really, really, really good about having lots and lots of public archives that are available not just to US citizens, but from people anywhere on the planet. The National Science Foundation in the US is getting there. Europe is catching up. There's sort of uneven results for other countries. But there's so much data. NASA data alone will keep you busy for a really long time. And when I'm talking about NASA data, NASA has lots and lots of data from, NASA does Earth observing, and they do observations of planets, like sending rovers to Mars, and there's NASA Astrophysics, which is telescopes looking out past the edge of the solar system. So there's lots and lots and lots of NASA data. I'm going to focus on astronomical data because that's what I do, but I wanted to call your attention specifically to all the moon and planetary data that are out there. Emily Lakdawala is a person who works at the Planetary Society, and she is an enormous supporter of these programs that get planetary data into the hands of so-called amateurs. There's some really amazing stuff that these people who are supposedly amateurs are doing, because a lot of these planetary data archives, the data are public as soon as they come back from the spacecraft. So the scientists are getting them at the same time as anybody else who goes to the website. And so there's a huge community of people who jump on those data as soon as they arrive. And so they make these absolutely marvelous images from the planetary data that's coming back. So Emily Lakdawala has many tutorials that cover how to get access to those data and how to work with those data, because that community has different conventions than either the Earth observing folks or the astrophysics folks. So I just wanted to call your attention to that. I'm not going to talk about that anymore today, so I'm going to really focus on the astronomy data. So archives are super valuable, and we have the data now that tells us that for any given astronomy mission, if you have a good archive, it can double the amount of science you get from your telescope. So the first plot there is the fraction of papers that are produced using Spitzer data, and the x-axis is time. The blue data, the blue wedge, is people who are writing papers about data that they themselves propose to get. The green wedge is papers that are using data that were found in the archive, not requested by the people who are writing the paper. And the red wedge is people who are using both PI data and archival data. And you can see, even though this plot stops at 2017, you can see that about half of the papers are using just archival data and have been for quite some time. It's not just Spitzer that is like this. Hubble is the other plot on the lower right. It too has, rather than fraction of papers, now they have total number of papers. And you can see there too that a good chunk of the papers that are produced using Hubble data are using Hubble archival data. So that's the value. If you have a good archive, then you double the amount of science you can do with the telescope. So the archives are, of course, designed for the professional astronomy community. But these archives are usually designed to be easily accessible, and that has to be easily accessible to astronomers of all kinds. An emeritus professor who can barely read his email, all the way through a summer student starting her very first research project. So those archives need to be accessible to all of those people, which means it's available to anybody who knows where the website is. You can get into it and use it without trouble at all. But you do have to reach across the barrier, by which I mean you have to become familiar with conventions and jargon and file formats and units, and you need to learn about the data that are produced from any given mission. So it's not going to be packaged up for you with a nice little ribbon on top. The images that you see for press releases often have some massaging done to them to make them look pretty for press releases. And a lot of stuff that gets removed either when doing science or the next step of doing a press release are things like instrumental artifacts, things that aren't really in the sky, but the things that are a result of the telescope's response to light, for example. So you have to become familiar with what you're going to find in the archive and how to actually look at the data and understand what's going on. So one of the things you need to do is don't use Microsoft Internet Explorer as your default browser. Most astronomers are using Macs or Linux machines, so they're not using Windows. And because these astronomical archives are not swimming in money, they have to limit what they're supporting. And since so few astronomers use Internet Explorer, there's not a lot of effort put towards making these archives compatible with Internet Explorer. So the first thing you want to do is go get Firefox or Chrome. Don't use Internet Explorer to access these archives. So NASA has several different archives. At IPAC, where I work at Caltech, there are 4 different NASA archives. There's IRSA, which I work for, which is the Infrared Science Archive. NED is the NASA Extragalactic Database, the NASA Exoplanet Archive, and COA, which is the Keck Observatory Archive. Is all 4 of those are NASA archives based at IPAC. Space Telescope in Baltimore, Maryland has MAST, which is NASA's home for UV and optical and some IR data. Goddard Space Flight Center in Maryland has HEOSARC, which is the High Energy Archive, but also the Cosmic Microwave Background Archive. And then in Boston, Massachusetts, at SAO, the Smithsonian Astrophysical Observatory and the Center for Astrophysics, there's an archive called ADS, the Astrophysics Data System, which is all of the literature in astronomy worldwide from the 1600s through this morning. And it's all accessible, all searchable, really fantastic. And then CFA also has, and SAO also has, the Chandra Observatory Archive. So IRSA is the Infrared Science Archive, and our charter is to provide an interface to all of NASA's infrared and submillimeter datasets, which means from about a micron to about a centimeter. It was founded in 1993, and it was the original home to IRAS data. IRAS was a joint British-American mission that flew in 1983 and was the first all-sky survey in the infrared. And IRSA was founded to be the home, the archive for that data. More than 10% of all referee journal articles written today use data that ultimately came from IRSA. So we have a lot of useful data in our archive. We have nearly 5 petabytes of images. So a terabyte, there's 1,000 terabytes and a gigabyte. 1,000 gigabytes in a terabyte, 1,000 terabytes in a petabyte. So, and we have 5 petabytes of images and 240 terabytes in databases. We have all-sky coverage in 24 different bands. Many of IRSA's tools have a similar look and feel because they're written with the same underlying software, and that software is called Firefly. It provides interactive tables and plots and images and overlays so that you can really explore the data that we have at IRSA. So I'm going to give you more of a demonstration in a minute, but I wanted to just show you this quick screenshot because a lot of the IRSA tools are going to have the same look and feel. So we've got an image in the upper left, and all those red boxes are a catalog overlaid on the image. On the right-hand side, upper right, we've got the catalog itself. And on the bottom, we've got a plot made from that catalog. And they're all interactive. You can click on a source in the image and see where it is in the plot and in the catalog. You can click on a source in the plot and see where it is in the image and the catalog. So some examples of some projects that you could do with IRSA tools. You probably have a favorite object. So what is bright and what is faint in images of your favorite object in each one of the wavelengths that is available at IRSA? Is it going to be the same things that are bright in each one? We have some optical data and then a lot of infrared data spanning a wide range of wavelengths. So Go get an optical image of your object, go get an infrared, a near infrared image, a mid infrared image, and a far infrared image. And is it the same things that are bright in each one? There's a lot of astrophysics buried in that. You could go get a Messier object of each of the broad types of objects that are in the Messier catalog, like pick a nebula, pick a globular cluster, pick a galaxy, and do that same sort of exploration. What does it look like across the wavelengths? And depending on which Messier object you pick, you may need to request wildly different sizes of images. So there are some classes of Messier objects that are going to look very different in the infrared, and some are going to look quite similar in the optical and infrared. You can, if you have access to a telescope that you took data from, you can make a 3-color image that uses your image as one of the color planes. In order to make this work, you actually have to have astrometry in the FITS header, that the world coordinate system. In other words, you have to have a way to tell the computer how to translate pixel number to position on the sky. And the way that it does that is astrometry. And if your FITS image doesn't have a FITS header with this information, you need to add it. And there's a website called astrometry.net, not astronomy, but astrometry.net, that will allow you to attach coordinates to your FITS image. Also, of course, IRSA's YouTube feed has many movies on tools like Find Your Chart, which I'll show you in a minute, and all the other tools at IRSA. IRSA's YouTube feed is linked from the bottom of the main IRSA homepage, or you can type in that long, complicated URL. There are many different playlists at the IRSA YouTube feed. You should not treat the playlists as really playlists. In other words, they're not trying to collect images or videos that will tell a coherent story if you listen to all of them in order. I'm treating the playlists at the IRSA YouTube feed as sort of tables of contents. So like all of the movies pertaining to Sophia are collected in one playlist and that sort of thing. So this is the IRSA homepage. You can find us by Googling, but you may need to convince Google that you're not interested in tax information in the US. Go to the IRSA homepage, and there's a couple of things right off the bat here. This tool will give you an indication of any data sets we have at IRSA that overlap the position that you give it. And this is sort of a broad catch-all net, but probably is not the best place to actually start. The search catalogs here is another interface to the catalog search tool. There's IRSA Viewer, Find Your Chart, and if you want to write your own code to interact with the archives, you can do so using VO Protocols, API's application programming interface. Then there are more tools down here that correspond to individual data sets from individual observatories. But for new people, I recommend that you start with Find Your Chart because it gives you the same chunk of sky in several different wavelengths. So I study star formation, so I'm going to put in M16, the Eagle Nebula. So I put in the name, and it figured out what the coordinates are. It tells you below the box what the coordinates are that it thinks you've entered so that you can check and make sure that it's understood you correctly. Because if you stop typing in M1, it's going to give you a different position than M16. You can use either NED, the NASA Extragalactic Database, or Simbad to turn the names into coordinates. Next, you want to pick an image size. 300 arcseconds is the default, probably good enough for this. Display size, if you're on a laptop, you might want small, or a big screen, you might want large. Then you can pick what image set you want. So DSS is the Palomar Observatory Sky Survey digital sky survey. So it's digitized sky survey plates from Palomar and another second telescope in the Southern Hemisphere. The Sloan Digital Sky Survey surveyed not all the sky, but a big chunk of it in the Northern Hemisphere. 2MASS is the 2-micron all-sky survey. That is all sky. WISE is the Wide Field Infrared Survey Explorer. That is also the whole sky. The Spitzer space telescope was a pointed mission, so it didn't do the whole sky, but it did a lot of the sky. And there were two main parts to the Spitzer mission. The first part where we had cryogen and all of the instruments were operating, and then the second part where we had run out of cryogen and only the shortest 2 wavelengths of IRAC were operating. So SEIP is the Spitzer Enhanced Imaging Products, and right now they are just the data taken when we had cryogen on board. It does not yet include the considerable amount of data taken after the cryogen ran out. Akari was a Japanese mission that surveyed the whole sky. They had a couple different instruments on board. Their longest wavelength instrument, FIS, has images that they've released of the whole sky. So you can search on Akari as well. And then IRAS, I mentioned earlier. IRAS is the infrared astronomical satellite. And the specific data set that you're looking at here is IRIS, which is a particular processing of the IRAS data. And that is also the whole sky. But it was the very first all-sky infrared survey. So you will see in a minute just how low the spatial resolution is. So when you're first starting out, I recommend that you turn off the catalogs because it can be overwhelming very quickly. Search. So it's coming back with the same chunk of sky from all of these surveys. It's the same size and they're all oriented properly. The changes there are coming as it's continuing to load in images. I think it's done loading now. So you can see here that we've got DSS. So they're scanned photographic plates. These two were taken in the 1950s. These were taken in the 1980s. Then we've got 2MASS, near infrared, taken in the late 90s. Now you see the data stop. The 2MASS tiles are really, really small. So you will frequently run off the edge of the tiles in Finder chart. And then all WISE, all sky survey. So there's a WISE 1, WISE 2, WISE 3, and WISE 4, which is 3.5, 4.5, 12, and 22 microns. JH and K are 1 to 2 microns. And then we've got Spitzer, SCIP. So IRAC 1 and IRAC 2 are very similar wavelengths to WISE 1 and WISE 2, so 3.5 and 4.5 microns. IRAC 3 is 5.8 microns, IRAC 4 is 8 microns, and MIPS 24 is 24 microns. So you can see it's the same chunk of sky, right? The fingers there, they're the talons of the eagle in the Eagle Nebula, and you can see the fingers in the DSS images. They're really not obvious at all in 2MASS, and they're starting to become more prominent in WISE. And in Spitzer, you can really see them quite obvious. Now, we've got Akari. So you can see they're very long wavelengths, and the pixels are very big in comparison to the other missions. And then IRAS, the pixels are enormous, right? It's the same chunk of sky. It's all lined up, right? So 60 microns is bright here. It's that same chunk of sky that's bright in a lot of these other things. This is all reverse grayscale. So white is the black sky, and black color in these images is bright. So all of these are, you're interacting with the actual images. So they're actual FITS images, not JPEGs, not PNGs, not representations of the data, but actual FITS files. And so there's a whole bunch of tools you can use at the top that allow you to interact with the images. So for example, you can zoom in or zoom out, or set it so that one pixel on the screen matches one pixel in the image. You can zoom them to fill the image, the box that you have. You can make them large enough to match the box left, right. So this chunk of, this image here, it's outlined in orange. That's the current image. So because these are locked together, anything I do to the current image is done to all the other images as well. So if you want to change the color table, you can do that. If you want to change the color stretch, you can do that. You're not actually changing the data. You are just changing the representation of the data. And depending on what you want to bring out in the image, you might choose a different stretch or a different color table. Because this tool is called Finder chart. And so people really do use it at telescopes. And so you can, if your telescope has a particular rotation where north is not up, you can change that. You can put it back north up. And some telescopes flip things, so you can flip on the y-axis like this. This asks you, if you're moving the images off and you want to recenter them, it'll center back on the target that you asked for. I'm going to skip the select an area for a second. This is a ruler, so you can measure the distance between things on the image by clicking and dragging. It's given me the length in arc seconds there. So there's 88 arc seconds approximately between those two stars. We can change the units on that if you want. Here is the layers icon. So the layers are showing us everything that we have overlaid on the image. So I'm going to select this one. So that's outlined in orange. Now the layers is going to give me all the layers that are overlaid on that selected image. So I've got the underlying image, the target that I searched on, and then here is the distance tool where I can change the color if I want, or I can tell it I want the position angle. Oh, that's interesting. You can measure, you can tell that you can change the units of what's displayed. Although that's interesting that it completely killed it. It doesn't usually do that. Okay, so you can also add markers. If you're planning observations, you can overlay footprints from a variety of different telescopes, or you can just add a regular old marker on the image. You can add a compass rose, you can add a coordinate system, you can read in DS9 regions files. So DS9 is another popular imaging program, and you can create overlays in DS9, and those overlays will also work on the images here. There's the layers icon, which I already mentioned. You can also change colors and delete from here. This turns everything back to the defaults. This locks color changes and overlays. This one locks position. Since this is Find Your Chart, all the images you're getting are of the same position, so that's why that's locked. If you want to see more information about each image, here, this one I've highlighted in orange, and the FITS header is there. And this is an interactive table, so you can search it or sort it, do whatever you need to do to find the keywords that you're looking for. Okay, so let's go get some catalogs to add in. Let's go back over here. We'll leave it at M16, but now I want to say search the corresponding catalog. So by default, it's assuming you're carrying just about the target in the center where you've asked, but for this example, let's change it to search within the image boundary. So it's going to go the images it already has. Basically, it's just pulling that out of the cache, and now it's going to go get the catalogs too. So I didn't find any IRAS sources in this region, not surprising because it's a tiny chunk of sky. I don't think it's going to find any Akari sources either, but we'll give it a second. It should find a bunch of Spitzer sources, a bunch of WISE sources, and a bunch of 2MASS sources. It won't find any Sloan data because there isn't any Sloan data of M16, so I might as well just close that. So it is loading the images very slowly. There we go. So we've got a 2MASS image in the background, and then all those green squares are the bits, the objects from the catalog overlaid on the image. So you can see why I told you to turn it off initially, because it is overwhelming. And the same thing is true for WISE. There's a catalog that's overlaid on the images there. The DSS images from Palomar do not have a catalog that go with them, but pretty much everything else does, although it's not. It found one Akari source. There you go. One Akari source right there. And no IRAS sources in this tiny chunk of sky. Okay, so then the purple boxes there are all Spitzer Enhanced Imaging Products sources. So the plot it's given on the lower right is a plot by position, which is kind of boring and seems kind of silly given that we have the catalog overlaid on the images here, but that is kind of the idea because you've got interactive things. So if you want to see where this source is in the catalog, oh, it's a 2MASS. Let's get 2MASS. Then it will jump to that source in the plot and in the catalog. But you can change what is plotted. You can say, let's do something slightly easier first. Let's say I only want the things that have really high quality detections. So things where the signal to noise ratio in J is greater than 10, and things where the signal to noise ratio in H is greater than 10, and things where the signal to noise ratio in K are greater than 10. So we've imposed filters, and now we have many fewer sources in the catalog, in the plot, and overlaid on the images. We only have the good detections. We can also change what's plotted as soon as it actually loads. Okay, so let's change what's plotted. We go to the gears, and it's going to come up first with a plot style question, and then it's going to ask what we want for the X and Y axes. So for the X axis, let's do J minus H. So the columns in the catalog are J underscore M. Now, if you don't remember, I use these catalogs all the time, so I know what the columns are. But if you don't remember, you can click on the magnifying glass and it'll give you a list of all of the columns in the catalog. But we actually want is not just a value from the catalog. We want to do J minus H. And then for the y-axis, we want to do H minus K. Okay, so now we have a color diagram. As soon as it plots it, now we have a color diagram of the sources that are high signal to noise in this region. So now, if you want to look at, gosh, that's a really, really red source. Let's click on that. There's that source, and here's where it is in the image. Let's see if we can make it bigger. So we're going to look at just one image at a time and zoom in a little bit. Come on. And move that around. So there is that very red source. So you can interactively explore the catalog and the images. If you want to stop all the filters you have imposed, you can click on Cancel Filters, and it will cancel the filters that we've imposed from all of these different places, and it will give you, again, the whole catalog in the plot and on the image and in the table. Let's go back to multiple images. So you can do that. You can't yet do that across catalogs, and so if you want to, say, make a plot that combines Ys and 2MAS, you'll have to make your own catalog in IRSA table format and load it in to make the plot. At the moment, it can only plot things from one of these catalogs. So that's the basic idea. The plots and the images and the catalogs are all interlinked. Let's go to IRSA Viewer. So IRSA Viewer is another version of the same kind of Firefly tool. But unlike Finder Chart, which gives you a chunk of sky from several different surveys that are all, very, very constrained, this gives you something more unconstrained. So let's, just for kicks, do M16 again. And then instead of 500 arc seconds, let's do 20 arc minutes. Okay. Now, the next part is fairly overwhelming because there's just truly an amazing number of data sets that are available in here. And rather than trying to read all of them and figure out what they are, you should use these filters on the left. So for example, if you're mostly interested in Ys data, if you click on Ys, it only limits you on the right-hand side now to the stuff that's from Y. So if I click here, I'm going to select all 4 bands. I can choose just one or all of them. Okay, so let's unclick that. So the Ys is still in there and still selected. Let's look at 2MAS. So remember I said a few minutes ago that the 2MAS tiles are really tiny. That's because in the late 90s, that's what the computers needed to be able to handle it, is little tiny tiles. And now things are faster. So instead of doing the tiny tiles from all sky, let's do 6-degree mosaics, because those will be a bigger chunk of sky, and it's be much less likely that we'll hit the edge of a tile. Let's unclick that. And let's go for Spitzer 2. So Spitzer has a lot of projects that deliver data. So SEIP, remember, is the Spitzer Enhanced Imaging Products, which includes all of the data taken when we still had cryogen. So if you want data taken from the considerable second half of the mission, where it was just the shortest 2 bands, you want to do research into figuring out which one of these programs you need, or you can start to use the filters here. So I know that M16 is in the galactic plane. So if I click on galactic, now I only have the Spitzer programs that are also galactic. And you see it's a much shorter list. So let's do glimpse, because I'm pretty sure that M16 is in part of glimpse. Okay, so we've selected a bunch of things. Let's go search. So now it's going to load in, or at least attempt to load in, all the images that we requested. So now you can see, even just at a glance, that they're not all the same orientation. Let's change the color table. Let's change it to reverse grayscale. And now let's pick 2MAS J. So I'm going to click on that. It's outlined in orange. And I want to say Align and Lock by WCS. This happens automatically in Finder Chart because Finder Chart is constrained to be the same chunk of sky. IRSA Viewer, you can go back and load as many images as you want from different parts of the sky. So it's not locked by default. The glimpse tiles are generated in galactic coordinates. So that's why they don't come up by default in the same orientation as the rest of them. So now we've got the same chunk of sky in many different wavelengths. Let's Finder Chart. One of the nice things about it was that it was ordering the images we got by wavelength. So go up here and choose the table icon. This is an interactive table, just like all the other tables in Firefly. So if you click on wavelength, it sorts the images by wavelength, not just in the table, but in the display as well. So if you want to, say, use this to compare what Messier objects look like across many different bands, this is how I would recommend doing it. And then when you sort it by wavelength, it becomes much more obvious that the long wavelength stuff is mostly seeing the interstellar medium, and the short wavelength stuff is mostly seeing the stars. Here you can make catalogs and plots as well. You go to the Catalogs tab, and you have access to a lot of different catalogs. Let's get, you pick Polygon, you can tell it I want sources over the whole image or subsets thereof. I'm going to go and get the All-Wise source catalog. Okay, so it's overlaid the catalog on the images, it's made a plot for us, and it's put the catalog over here. So again, it's pretty overwhelming. Let's do some filtering. Let's get this down to just the high quality detection. So greater than 10 signal to noise ratio in WISE 1, greater than 10 signal to noise ratio in WISE 2, greater than 10 signal to noise ratio in WISE 3, and then greater than 10 signal to noise ratio in WISE 4. Many fewer sources. Let's do one image at a time. There's J. Okay. So now we can change what's plotted too. Here we can actually change, we have more flexibility in, well, we have more flexibility in all of these panes than we did in Finder Chart. But here we can change what's plotted just like we could before. So J up, J minus H. Why is that not working? Oh, because it's a WISE catalog. Silly me. W1M Pro minus W4M Pro. And then W1M Pro. Okay. So there we have a color magnitude diagram. But conventionally, you want the bright objects at the top. So reverse the y-axis, apply. Now we have an infrared color magnitude diagram. Here too, you can pick the very reddest things and see where they are in the table and in the plot. Come on, you can do it. I don't know why it's not. There we go. It finally worked. Okay. You can also make different kinds of charts. So instead of a scatter plot, maybe I want a histogram of all the WISE 1 brightnesses. And there it is. Okay, I haven't shown you stuff about the selection yet. So let's cancel the filters. Let's get rid of that plot. Let's go back to viewing just the images big. Okay, so maybe what we want, let's do one image at a time. So let's say we only want the sources that are in, you can't see her, but my cat is affecting the mouse. Very sorry. You can see that dark region here. So let's go to selection. So if I pick this, okay, it gives me many choices. So one of the things I can do is I can filter down the catalog so that it only includes sources from that region. And we can cancel the filters. We can select a portion of the image and do statistics on it. And here, if we put our mouse over it, it will overlay. You can see a tiny red. Here, let me turn off the catalog. It'll make it easier to see. Let's turn off the catalog. Okay, so now that little red X that's in the lower right of the box is where the faintest thing in the image is. That's where the brightest thing in the image is. That's where the center is of the pixels in the aperture, and this is where the flux weighted centroid is. So you can do some simple photometry this way, but I don't recommend it in general. If you want to crop the image, you can do that. And then you can, for example, save that cropped image to disk. Let's return everything to the defaults and go back to the default view. Oh, we need to turn the catalogs back on. So the selection criteria can do a lot of different things. You can, like I say, crop images, select portions of the sources in the images, and so on. Okay, going back to the main IRSA page. We've covered IRSA Viewer and Finder Chart. The catalogs interface is like this one, but it is accessing just catalogs, not the images. So you can more easily, I think, access the catalogs from within IRSA Viewer, but if you want to get into just doing catalog selections on your own, you can use that tool. The other stuff down here is a lot of really good documentation, as well as data that aren't yet available in some of these other tools. So the Spitzer data, if you go here, find basic information about Spitzer, lots of good things to learn, but then all of the information about all those different projects and what they deliver. This is why half the publications from Spitzer involve archival data because there are so many contributed products from people who use Spitzer. This is really phenomenal, and it's already reduced. It's already got catalogs, already got spectra. You don't have to do very much besides just get started on your science, but you do need to read all that documentation to figure out what it is that you're looking at. WISE similarly has a page with lots of documentation and lots of information about all the different portions of the mission and then all the different deliveries of data products that they have. SOFIA is our newest archive. SOFIA is a plane with a hole in the side. It takes a lot of infrared spectroscopy. So they do not cover large chunks of sky, but you can see this interface is very similar and will allow you to search the SOFIA archive. Here, IRTF is another relatively new archive. This one also has an archive that allows you to search the delivered data that they have provided. TUMAS is here. Herschel was a European mission. Again, documentation, all these places. Planck is a very long wavelength mission. Again, lots of documentation and stuff to look at. IRAS, we've already talked about. MSX is actually an Air Force mission. And they surveyed the galactic plane, and so there's a whole bunch of data there. ISO was a European mission, lots of data from there. SWAS is a submillimeter satellite. ZTF is time series, so their telescope is based at Palomar, so if Palomar can see it, they probably have at least several images of it, if not many, many, many. CARI we've talked about. Cosmos is an extragalactic research project that has data from huge numbers of wavelengths, and all of their data are available through IRSA. BLAST is a balloon-borne mission, so we've got some data here. Bolocam is a ground-based millimeter observatory, and so there's lots of data there. And IRTS is also a relatively old mission with lots of data. So all of these links go to pages that have documentation, explanations, background, access to the data. There's lots and lots of documentation online. There's video tutorials I mentioned earlier that are available here. And then there's the help desk. So if you have questions, you can mail us there.